Hello, everyone. Thank you for joining me. My name is Davide. I'm a business intelligence consultant with Dundas, and this is Predictive Analytics for Everyone. We're going to be highlighting some of the various predictive analytics capabilities that are available in the newly released Dundas BI 5.0. Throughout the webinar, please feel free to ask questions via the GoToWebinar panel. And we'll be able to get back to you on those and answer them as well. All right, so let's get right into it. So before we get into the meat, let's quickly talk a little bit about the application that we're using in general. So if you're new to Dundas BI, what it is an extremely flexible BI and analytics platform. It has a wide range of capabilities that allow it to serve as a true end-to-end platform that enables you to handle all your data preparation, data analytics, presentation, and advanced collaboration in one single platform. It includes a built-in administration layer that makes it very easy for you to control your infrastructure and your overall BI for your organization. And it provides a huge amount of additional flexibility via the various APIs that it makes available. So APIs for extension, for scripting, dashboards, and for white labeling and styling. So in today's webinar, we're going to specifically focus on the new features in Dundas BI 5 that cater to the predictive analytics possibilities, allowing you to intelligently analyze your data to gain insights about data that you don't necessarily have already. So Dundas BI 5 was launched last month, and it includes a whole bunch of innovative new features across three main categories: painless advanced visual analytics, simplifying the integration of the system so that you can work it into your existing business processes, and a superior user experience, making it easier and easier for users to make sense of the application and quickly get to the results that they're looking for. Again, today's focus is going to be looking at the predictive analytics features that were introduced in version 5, specifically some formula functions that are going to allow you to quickly perform those kinds of analysis on the data that you have, as well as the brand new Python integration that's going to allow you to leverage the various capabilities of the Python language and its data analysis libraries in order to more effectively analyze your data inside of the Dundas BI application. All right, so with all that out of the way, without further ado, let's jump right on into it. So here I have my Dundas BI home screen. So this is what the application looks like for those of you who are new to it. And we're going to start off by taking a look at the most obvious feature that someone thinks of when you talk about predictive analytics, which is going to be the ability to forecast future data based on your historical data. Now, in previous versions of Dundas BI, there was a whole lot of regression-based forecasting available, so the ability to extend a trend or get a regression curve. But what we've introduced in the new version is formulas that make use of the technique known as exponential smoothing in order to capture trends over time, weighted based on how recent they are, and also capture seasonal repeating fluctuations so that you can get a much more careful and granular pattern of what you're looking for. So let's go ahead and play around with that a bit. So I'm going to bring in some sales data here, some sales numbers, and I'm going to separate those out by the quarters. So I end up with I end up with this line here that's showing me that data. And so if I want to simply see what my likely sales is going to be in the next quarters after this data ends. The way that I can do that very simply with this new formula is I can hit this add formula button, and then I'm going to be able to use this new forecasting function. So that's right here. It auto completes for me. I select that forecasting function, and then I can see what arguments it takes. The first one is it wants me to tell it what time axis to use for the prediction, and then the second input is it wants me to let it know which of my measures it's supposed to extrapolate. So I'm going to go ahead and click over on my date axis there in order to tell it to use that date axis, and then I can click over here on my line to tell it to use those sales values. And then I can close that off because the rest of the arguments of this function are optional. So let's go ahead and apply that. And what it's going to do is it's going to run through the various points in this data set. It's going to look for any repeating patterns. It's going to look for the overall trend, the curve of the trend, and it's going to append a forecast onto my line, which shows me where it thinks those numbers are going to go in the next several quarters. Now let's touch quickly on some of those additional arguments that we were able to provide. The first one allows me to customize how many periods into the future the forecast goes. By default, it goes about a third of the, by default, it'll basically take a third of the length of your data set and predict for that amount. But if you need less, then for example, say we only want to predict 1 year out, so that would be 4 quarters. We can go ahead and do that. We end up with our 4-quarter forecast, or maybe we're looking for a crazy long prediction. Let's go with 20 quarters, 5 years of forecasting, and that's what we end up with right there. And then the last argument that this function can take is you can actually define what's known as a season length. So notice these repeating patterns here that it was able to pick up from our data and incorporate into the forecast. So this is what's known as a seasonal pattern. And in this case, because our data is quarters, our season is basically 1 year or 4 of those quarters. And it's very clear that our data does indeed follow such a 4-quarter pattern, and that's reflected in the forecast after the fact. But if we had some additional information outside of our data that causes us to think that the season length that was guessed by the application was not the one that we want, or if we know our season length in advance, there's no reason why we shouldn't supply it, because that's just going to make it easier for the forecast to be more accurate. So if for some reason I knew that the real season here is 3 quarters, then I could put that in. Obviously, that's not going to help this forecast because that doesn't actually match this data. If, for example, I decided to go with 8, it's going to give me something a little closer. 8 quarters is still not really the season that this data uses, but at least it's a multiple of 4, which is the actual one, so it gets close. In reality, in this case, the best answer is 4, which is what it had guessed automatically. Okay, now this is the forecasting formula. It provides a very simple interface to our exponential smoothing functions so that a user that isn't overly familiar with exponential smoothing techniques can quickly and easily make use of it. But we do offer a whole bunch of additional functionality surrounding that that we can get into. And that is hidden behind a different formula that has a far larger number of arguments. And before we totally get into that, I just want to show you one more thing that we created in order to make it easy for you to try and get as much as you can out of this functionality. And that is that under the Revisualize menu right now, as long as I have some data over time, it's going to provide me with this forecast analysis tool, which is actually going to automatically make use of some of those more advanced functionalities to get me a more complex forecast without demanding that I do too much or know too much about the overall techniques being used. So let's go ahead and take a look at what happens when we try that. And so what it's done here is it's actually given me my forecast, and in addition, it has also given me this confidence range. So basically, it's showing me the forecast, and it's showing me a range within. It's 95% confident that the future data will actually fall within that range. If we look over here at our metric set now, we can see that that it's actually added 3 new formulas into our KPI here. The first one is the main forecast, and then the second 2 are the 2 sides of the confidence interval. I'm going to quickly hide that confidence interval for now so that we can focus in on the forecast specifically. So let's go on into that formula. And we can see here that we're using a different function than we did before. Instead of forecasting, we're using we're using EXP smooth. Now this is the variant of the formula that works for more advanced users. So if we look here, we can see I've got here the list of the different arguments and what they do. So we've got the first few are the same as we had before: the time axis to use, the measure to use, the length of the forecast. And because there are so many different arguments here, we've made an effort to make it so that whenever you put a -1 in any of the optional ones, it'll refer back to the defaults, so that you can set exactly the arguments that you want and then ignore all of the rest. So let's go through and talk a little bit about what some of these do. So we're familiar with the season length. It's set to automatic currently, so it's going 1/3 of the normal data set length. So now for the, so that's the forecast length. For the season length, it has selected 4. And the other cool thing about the forecast analysis tool is that what it'll actually do is it'll run the automatic optimizer for the function once, and it'll actually take the results and physically put them into the definition of the formula. And what that does is it prevents us from having to run the automatic selector subsequent times, and it also allows us to easily see what values the optimizer has chosen for our particular data set. So we see here that it's chosen 4 quarters as our season length, which we had discussed why it's important to have that right. It's got this -1 here for the confidence level, which is the probability that we're aiming for with our confidence interval. So let me quickly show you how that has an impact. So the default for that is 0.95 or 95% confidence. Let's go ahead and show our confidence intervals again. And I can show you what happens if I go into one of these and let's say I decrease that confidence level to, let's say I only need 75% confidence. Hold on. I think length of the forecast, probability, hold on. 0.95. All right. Oh, I see. Let's bring that up to an 8 there. So what that does is it'll, so what I can do now is I can actually change that to an 80% confidence, and it actually will tighten it will tighten that interval here. And then if I do that on the other half of the range, let me just take these values, then I will similarly see that move that way. Oh, I need to change that to be lower. There we go. So I now have this tighter range with 80% confidence that my forecast will fall inside of there. So depending on how much confidence you need it to have, and how narrow you how well it's able to, how confident it is in its ability to pick up the patterns from your particular data set, those values there are going to change. Moving forward, the next one that we have here is we have the ability to change whether we're showing all the results. So right now we've got this nice easy situation where we've got our main data, and then as soon as it ends, our forecast starts and continues from there. But the truth of the matter is that what's actually happening is behind the scenes, it's actually attempting to forecast each point in the data on its way to the end, and that's how it's able to determine which of these other settings are the best based on which ones are able to predict these points the best, and that's also how it's able to determine that confidence level. Because if we set that over here and over here, then we can see that we actually have that confidence range the whole way through. And the way that it's able to determine that it's 80% confidence is that it's probabilistically able to capture about 80% of the points in there based on the average variance that those values have. Okay, so let's go back to hiding the intervals so we can continue to focus on the forecast itself. So next up, we have the, this here is an option, is the number of optimizer passes. So this basically decides how hard the optimizer is going to work to find the best values in order to fit your data. So if you find, if on a really huge data set, you want, you're finding that it's taking a little too long and you want to speed it up, you could reduce those. Or if you're finding that it's not accurate enough and you need some more time, you can increase that number. Generally, in our testing, we found that this default of 10 passes was a great sweet spot that's fast in almost every case and accurate in almost every case. The next up, we've got this trend smoothing type and season smoothing type. I'm not going to get into a huge amount of detail about what these are. Suffice it to say that exponential smoothing has several different variants based on different things. So let's quickly go through a simple example here. So there are three main subsets of exponential smoothing. The first version is called single exponential smoothing, and that's where it only takes into account, it's basically a weighted average of your data going up this way, and then it eventually meets that level there. So that's the most basic version. Double exponential smoothing is when we start to take a weighted average of the trend between your points as well. So a weighted average of the difference between different points as we move forward. So at this point, we're now able to actually project the direction in general that the data is overall going to go. And then triple exponential smoothing is when we're able to look at those seasonal trends and we start taking various weighted averages of the relative positions of points in a season. So that goes over here. And then within these different types, you've got, within your trend smoothing, you've got different variants such as this one here is additive, but we've also got additive damped, we've got multiplicative damped, and under season we've got additive and multiplicative. I'm not going to go into a huge amount of detail on the actual mathematics behind that. If you're familiar with them, then you can make use of these arguments in order to fine-tune how you want this to model your data. But the nice thing is it can actually choose those for you automatically, which I believe in this case, it had chosen the 3 and 1 approach, and that's what it gave us there. And then the last the last 4 arguments here are alpha, beta, gamma, and phi, which are, again, a little bit wonky and get into the nitty-gritty of how exponential smoothing works. Let me bring that back up. So I'm not going to go into detail on what those are, but if you know what they are, then you'll be able to adjust them, but most people don't. These 4 elements in particular, in basically any case where people are using these techniques, they will have those automatically determined by an algorithm, which is exactly what we've done for you here. We've found the alpha, beta, gamma, and phi that work best for projecting this data set. All right, so that's exponential smoothing, and that gave us all of that. So next we're going to move on to clustering, which is a very popular and simplified, a very popular basic case for machine learning. So let's go ahead and start a brand new metric set. And I'm going to bring in a simple data set that is very specifically able to show you what this clustering does for you. So we've got these various IDs and these X and Y values. And with that, we're able to get this point chart of all of these different values. And you'll notice that they clump up in various different places. So the purpose of a clustering algorithm is for it to be able to identify distinct clusters within a set of points that have various numbers of positional measures. So it could be 2, 3, 4, any number. So let's go ahead and take a look at how Dundas BI is going to enable us to classify or categorize these different data points into their clusters. So let's go add formula, clustering, and then we've got our X and our Y. So the first thing it's done here is it has taken the results of my clustering and put it as a new series at the bottom there. If I bring up my data preview, I can see a little more clearly that it has assigned each of these data points a cluster ID to tell it which cluster it goes into. I don't want to display that as a new series on there. So what I'm going to do is delete that series. So now I'm just left with my original points. And what I'm going to do is actually bind that cluster value to the color of my data points. Now, in the general case, usually when people bind a measure to the color value of one of their series, they want to see a nice smooth gradient of color to indicate the change in value. And that's all well and good, but in this particular case, we're much more interested in seeing sharp delineations of the different groups. And the way that we would be able to do that is we can set these various color rules instead of the automatic one that had been set. I'm not going to go through that whole process here because I've actually already done it. And I saved all of those rules into a style here, which I can simply bring onto my chart, and that's going to help us more effectively visualize those different clusters that the algorithm has identified. So from where I'm sitting, I think it did a pretty good job here. It grouped up all these pinks, all those. Maybe these 2 points are arguable that they could have gone with green, but overall, a really good job on that. So that's the basics of what clustering does for you. In addition to the basics there, you do also have the ability to specify what we call a K value, basically how many clusters there are supposed to be in the data. So there are 15 clusters in that data, and it was able to identify that. So if I give it the 15, it's going to look the same as this, just like that. If I, for example, ask it to give me only 10 clusters, then it's more likely going to group multiple together. So in this case, these two were made into the same cluster because it's not making enough clusters to give them all their own. Again, we do the automatic guessing for you, but if you have external knowledge about the data that you can bring in to help it more effectively handle your case, then you have the ability to do that. So let's actually take that, bring that into a more real world like example. So let's grab a new metric set again. And we're going to bring in this Fisher's iris data set. So what this is a series of measurements of various elements of flowers. And our goal here is going to be to try and identify flowers of different species. So let me quickly switch that to a point chart. And I'm going to, let's set our vertical axis as sepal width and our horizontal axis as petal length. So we can see here, we can see two of the measurements on our screen here, but the thing is there are actually 4 total measurements that identify these flowers, which is a little harder for us to look at, but it's no problem for the clustering algorithm to go ahead and identify based on those 4, based on clusters basically in 4-dimensional space based on that. A very hard task for a human because we can't even conceptualize 4-dimensional space visually. So let's go ahead and perform that clustering. So we can go clustering, petal length, petal width, sepal length, sepal width. So the nice thing is you're able to put any number of measures here into clustering. The only thing that identifies if your arguments are not going to be those measures is if you give it a static number, which it'll then interpret as your K. So let's go ahead and put that in. Once again, it gave us an extra series that we don't need. So let's go ahead and get rid of that. And as we did before, we can go ahead and bind our function onto the colors, and then we can bring in our style to identify the different clusters visually. So in this case, we notice that it's clustered this large chunk together and this chunk together, and then this large set of outliers together. Now, in this case, I'm aware that those outliers throw us off a little bit. Now, the algorithm attempts to find the first optimal value of K, so where it's able to find clusters with the greatest level of cohesion. Because there are these significant outliers that exist in these flower species that I know about, I'm actually going to allow it to have an additional cluster just because there are 3 species and I want it to throw any outliers that are going to throw it off into a final cluster by themselves. So I'm going to actually force that to cluster into 4 groups. And now we see this cluster over here, then this purple one here, and the green, and then it took those outliers there and put them out in their own cluster. So let's see how we did here. I'm going to throw this metric set out onto a new dashboard. And then I'm going to put that here, and I'm going to actually bring in another metric set that was made beforehand that actually has the correct assignment of each of the points to their species. So with a little bit, so with that assigned K, our clustering algorithm did a pretty good job of finding most of the members of each of those species there. Let's see the names. Oh, Let's bind it to those. That's got a whole bunch of color rules on it. I'll ignore that for now. But the important part is these three species names: I. setosa, I. versicolor, and I. virginica, right there. And our clustering algorithm, for all the normal members of each species, it was able to get all of the I. setosas, which makes sense because they're so different from the other two species. And then these two that are more closely mingled together, it got for the most part, with a couple exceptions. And then these outliers here, it had to throw into a different cluster. So that's the clustering algorithm and how you can use it in Dundas BI and what the kinds of cases it's able to help you with to categorize different groups within a data set. And so so following on that, let's go into one more topic, which is the brand new Python integration. So with that, I'm going to create a new Dundas BI data cube. And I'm going to go ahead and bring in that Fisher's iris data again. So these are the same flower data that we had here. And I'm going to exclude the species information. And we're going to see if we can use analysis to figure those out. So I'm going to go ahead and make use of our Python analysis transform here. And I'm going to reveal here, so what I actually did prior to this webinar is I put together this Python script that used Google's TensorFlow library to create a deep neural network, which I then trained against a very similar data set related to these three species of flowers. And in that data set, it already knew what each of those flowers went to, so it was able to train and learn how to identify the patterns that make each of those species. So I was able to do that and save that deep neural network model over to a directory here. And then now I have another script here that's going to be able to take the results, that's going to be able to feed some data from my data cube into that model and let the neural network tell me which species is which. So let's play around with that a bit. So I'll go into my Python analysis transform. And the first thing I need to do here is set up what we call placeholders. And that's going to be how I'm able to reference data inside of the script. So I'm going to go here, I'll add a placeholder. So I need a placeholder for sepal length, so I'll do that. And so now it's telling me that I can use this identifier inside of my script to refer to that value from my data. So let's do that for the remaining items. Okay. Length. So looking again at this script, I've basically got this situation where I'm loading up my neural network model from that same directory where I had saved it to before. I'm going to construct an array of samples out of my various sepal length, sepal width, petal length, and petal width combinations. Then I'm going to use my neural network model to predict the species of those flowers, and it's going to use an encoding where 0 is setosa, 1 is versicolor, and 2 is virginica. And then I'm simply going to perform the translation from those numbers into the actual names, and then I'm going to package all of that into a final data frame to output into my data cube. So let's go and run that in my cube. So we've got all that coming out. It's identified the species that it thinks are right. So let's now go take a look how we did. I am going to do one more thing here because the application naturally will aggregate any numeric values into any grouping values that you use. So if I just use species, it's actually going to just sum up these various values for each species, which is not what I want. So instead, I'm going to give each of the entries in my data set an ID here using this rank transform. So now the order of the rank doesn't matter because I'm just using this to give a unique ID. Okay, so let's set that, and I'll set that. I'll set that sample ID as a and I need to set that as a hierarchy so that it'll group my measures in my metric set afterwards. Okay, so now with that complete, let's go ahead and return to our dashboard there. And let's see how the neural network does compared to the other ways. So let's grab that data cube that I just made. So I'll bring in my sample IDs. I'll bring in my species. And all I really, because the calculations have already been done, all I really need are my sepal width and petal length for displaying the points out on the chart. So sepal width. And petal length. Okay. And then the last thing I need to do is go ahead and bind my species to color. So in this case, we see the results. So we have here our result from our clustering algorithm, the true species of each of those samples, and then the last one over here is the result that was given to us by the neural network. So all of them did pretty well, better in some places than others. For example, the neural network was much better at identifying these further outliers. But I think it looks like the clustering did a better job with these intermingled values that were very close to each other. So one more thing I just wanted to touch on is we focused primarily on the Python analysis transform during this one, because that's going to be the more common case when you're doing these kinds of machine learning tasks where you're feeding in your data and performing some kind of analysis. In this case, I had a model that I had already trained in Python outside. Or if you're going to be using other kinds of libraries, it might be possible that you might have some kind of Python application that's already ingesting data and processing it, and then you just want to pull that data out. And in that case, we have what's called the Python data generator. So that's where instead of pulling data from a different source, we pull the data directly from a Python program. So that's another way of approaching it. But I think you'll find that the Python analysis is more commonly what you're looking for. All right, so that covers it for the material within the application. Let's go over here. So so what are your next steps here? If you want to learn more about Dundas BI, or if you're not new to Dundas BI, then you can definitely sign up for the next webinar that we're going to have coming up, which is 18 cool features of Dundas BI that data people love, on March 21st. If you're new to the product and you're interested in getting some more information, then you should definitely reach out to an account executive or a solution architect in order to book a full demo, or to generally gather some more information. And you can also try our free online trial on our website, or the free product download, which will allow you to install a Dundas BI server in your own location and play around with it however you want to. Now at this point, let me see what other questions we can have, what other questions there are that we want to go through. Is it possible to stop the forecasting formula at a certain value? For example, if you have a percentage fill rate and you want the forecast to stop at 100%, what you could do in that case is you could actually filter your data so that it won't go above a certain value. So all of the normal faculties of your metric set are still available. The function itself is not going to it does not have any arguments that will cause it to stop at the value, but you can absolutely put in filtering that goes based on that logic. So if you have a particular stop point, then you can set a filter that's going to exclude any values after you've reached that point. Can the clustering function handle categorical variables? So the clustering, clustering in general generally works with spatial representations of data. So that's going to have to do with numerical. It needs items to be in a particular order. So some kind of numerical order. If you have a series of labels that you know go in a particular order, so this one is adjacent to or similar to that one, is adjacent to that one, then you could assign those numerical values, and then you can feed the data into that one. If, on the other hand, you're referring to the idea of setting categories based on the output of the clustering function, that is something that you can absolutely do because the clustering function is actually also available inside of the data cubes. So if you use a calculated element transform, you can run the clustering function and you can use the output as a dimension, and you can even run a subsequent calculated element that will translate those numbers into names. So I had a question about how how the predictive analytics here compare to a particular other tool set. I'm not 100% familiar with that tool set, so that would have to be something that we discuss at a future time. All right, so if that's all the questions, then thank you everyone for joining us. You can direct any additional questions or comments that you have to info@dundas.com, as well as visit us at www.dundas.com, where we have plenty of information about the application and all the cool things you can do with it, as well as the ability to download the free download or use the free online trial, and also the ability to get in contact with us to request a demo if you're hungry for more information. All right, all of you guys, have yourselves a great day.